This is the section 5.3 in class notes, slides 16 and 17. All right, so on slide 16 and 17, we have two more examples of related rates problems. All right, so number 2, suppose a liquid is being cleared of sediment by pouring it through a cone-shaped filter. Assume the height of the cone is 16 inches and the radius of the cone is 4 inches. If the liquid is flowing out of the cone at a constant rate of 2 cubic inches per minute, how fast is the depth of the liquid decreasing when the liquid is 8 inches deep? All right, so first of all, we need to start with a picture, right? That is step 1. All right, so I draw a picture. So I have a cone-shaped filter here, okay? Now, the liquid is put into this filter, right? So then it flows out of the filter once it has been cleared of the sediment. All right. So now you are told what? All right. The cone is not changing its size. So that is important to note. So the radius of the cone is 4 inches and the height of the cone is 16 inches. All right. Those are not changing. So I do not give them a variable. All right. But what is changing? Well, you have a certain level of liquid in the filter, right? And so as the liquid flows out, the volume of liquid in the filter is changing. So the liquid has a particular height to it and a particular radius to it, right? If you look at the top of the level of the liquid, it has it's a circular thing because it's a cone. So it has a particular radius to it, all right? So now, as the liquid flows out, the height is changing. So there is a dH dt. And since the liquid is flowing out, then dH dt would be some negative value, right? Height, in this case, is referred to as up in here as the depth. And so that is actually what we want to know. So we put a question mark there, all right? Then the radius is changing. Well, then that would mean that there is some sort of dr dt, right, which is the rate of change of the radius, all right? And that is something that we also do not know, but we actually don't need to know it, and I'll explain why. All right? So now, what else do we have? Well, the thing that a lot of people forget is that we have a particular volume of liquid in the filter. And so as the water flows out, the volume is changing, and so there is a dV dt, right? And you are told that the liquid is flowing out at a constant rate of 2 cubic inches per minute. So dV dt is 2, but remember, the volume of liquid is decreasing, so that means dV dt is negative 2. All right, so we've drawn a picture, we've labeled everything, particularly the rates of change. So now we need to come up with our find statement. All right, find blank when blank. All right, so find what? What are we trying to find? Well, it says how fast is the depth of the liquid decreasing? So how fast is the height changing? So find dH dt. All right, when what is true? Well, it says when the liquid is 8 inches deep. So what would that mean? That when h equals 8. All right, and so that is our find statement. All right, so now we need to write an equation relating the variables. All right, so what are our variables? Well, h, r, and v. So the volume of a cone, right? So volume of a cone is 1/3 pi r squared h, right? You may remember that, maybe you don't, right? You would have covered that in geometry. Don't worry if that's not something you don't remember off the top of your head. All right, so v equals 1/3 pi r squared h. All right, so now what I want you to think about is, okay, the next step is going to be to differentiate with respect to time. Okay, so now if we were going to differentiate this, we have an r squared and we have an h, so we would actually need to use the product rule, right? And if I did use the product rule, I would get r squared times the derivative of h, so that would bring in the dH dt, but then I would have h times the derivative of r squared, which would be 2r dr dt. So now earlier I said we don't need to know that. Well, that is true. We do not need to know that. So what we actually want to do is we want to get rid of one of these And we will get rid of r because we don't want to know that. All right, so how do we do that? Well, what I want to do is I want to kind of take this picture and kind of redraw it over here, right? So if I draw half of the cone two-dimensionally, I have a right triangle, right? Where this is 4, the radius of the cone, and this is 16, right? But then inside of that, I have the liquid, right? Which has a radius of r and a depth of h. And so I actually have two similar triangles, right? And so what does that mean? Well, we can say that r is to 4 as h is to 16, which means that r is, well, if I multiply by 4, I would get 4h over 16, or h over 4, or 1/4 h, right? So what we can do is we can actually go into our volume equation and we can substitute r out. So I can say volume is 1/3 pi r, which is 1/4 h quantity squared times h, right? So now our volume is actually just a function of h. So v equals, so now if I have 1/3 pi and then I have 1/4 h squared, 1/4 squared is 1/16. So 1/16 times 1/3 is 1/48 pi, and then I had h squared and h, so h cubed. All right, so now this is the equation that we want to take the derivative of. All right, so now we're going to differentiate with respect to time. So take the derivative of the left side, dv dt equals, all right, what's the derivative of the right side with respect to time? So 1/48 pi, that's just a constant, so 1/48 pi times the derivative of h cubed, which is 3h squared times dh dt. Okay, so now 1/48 and 3, those reduce, right? 48 divided by 3 is 16, so this becomes 1/16 pi h squared dh dt. All right, so now we want to move on to the next step. It says plug in known quantities. All right, so what are the known quantities? Well, I know that dv dt is -2 equals 1/16 pi times h. Well, we want to know dh dt when h is 8. So h is 8. So 8 squared and then dh dt. And so now this is a relatively easy equation to solve for dh dt. So basically, I could multiply by 16. So I get -32. And then divide by pi and 8 squared. So divide by 64 pi equals dh dt, right? And so 64 and 32, those reduce to 1/2. So I get that dh dt is equal to -1 over 2 pi. Okay, but what? So remember, we want to be mindful of units here because these are in context. So we are talking about the rate at which the height is changing. The height is measured in inches, and the time unit is measured in minutes. So we would say -1 over 2 pi inches per minute. We do want to make sure we understand units in this section. All right, so that is slide 16. All right, and so then we have one more example that we'd like to do. All right, moving on to slide 17. All right, an airplane flew over an airport at a rate of 300 miles per hour. 10 minutes later, another airplane flew over at 240 miles per hour. If the first plane was flying west and the second plane was flying south, and both planes were flying at the same altitude, determine the rate at which they were separating 20 minutes after the second plane flew over the airport. All right, so we want to draw a picture. All right, so now what I'm going to do is I'm going to draw a point here. All right, and this is going to represent like where the airport is, okay? But we're looking kind of like, I mean, you say like bird's eye view, but really like from above the airplanes as well. So the airplane 1, all right, it says the first plane is flying west, right? So the first airplane crosses over the point where the airport is and then keeps going west, right? Okay, then the second plane flies over 10 minutes later, right? And it says it's flying south, right? So it flies south. All right, now, of course, if it's flying directly west and directly south, those two things are at a right angle, okay? All right, and they're at the same altitude. So there's not really a third dimension in play here. It's just these two dimensions, okay? All right, so now, what variables can we give here? Well, first of all, it says an airplane flew over an airport at a rate of 300 miles per hour. Okay, so this plane is flying at a rate of 300 miles per hour. Okay, but the question, first of all, is how far is the plane from the airport, or from the point directly above the airport? Well, I'm going to call that W, right? Just for like west, I suppose. All right. So now W is a variable, right? Remember, it is changing, right? The plane is flying, so that the distance that it is from that point above the airport is changing, right? Same thing with the plane flying south, so I'll call that S, right? That plane is changing its distance from the point above the airport as well. Now, how fast is W changing? Well, W is changing at dw dt, right? Which you are told is 300, right? It says an airplane flew over at a rate of 300 miles per hour, so that means that is the derivative of the distance, right? All right, and then the same thing is true with S, right? That distance is changing by ds dt, which you are told is 240 miles per hour, okay? Now, it says determine the rate at which they were separating. Well, we haven't put that in yet, but the distance between the planes would be right here. All right. And so I'm going to just call that capital D for distance. All right. So that distance is changing, right? So we have to give it a variable, and it is changing, well, at a rate of dd dt, right? And that is what we want to know. Now, keep in mind, as W gets bigger here and as S gets bigger there, that distance is growing, and so d dt would be some positive value, right? We want to make sure we keep that in mind. All right, so that is our picture, and all variables and rates of change are defined. All right, so next thing, all right, find statement. All right, find blank when blank. All right, so what does it say? Determine the rate at which they were separating. So that's what we've called dt. So find dt when what is true? Well, it says 20 minutes after the second plane flew over the airport. All right, so this is kind of interesting. 20 minutes. So a lot of people would just say, oh, t is 20. Well, that's not entirely true, because 20 minutes after the second plane flew over the airport. So I could say t sub S for south, right? That's the second plane. T sub S is 20 minutes, right? But T sub W, well, how long has the plane flying west been flying? So it says 10 minutes later, another plane flew over, right? So that means T sub W is 30 minutes, okay? So that's an important thing that we understand. All right, but now, here's another thing. Our rates of change, 300 and 240, those are given in miles per hour, right? So 240 miles per hour, 300 miles per hour, but now I'm dealing with minutes. So we actually do want to convert those. 20 minutes is 1/3 of an hour, right? And 30 minutes is 1/2 of an hour. So it is important that we understand that we do want to change those units. All right, so anyway, how are the variables related? W, S, and D. Well, this is actually just a Pythagorean Theorem problem. Okay, so W squared plus S squared equals D squared. Now, another important thing to remember, well, is that all of those are variables, right? Remember, in our earlier problem, the ladder problem, the hypotenuse was not a variable, so we put that number in right away. But these numbers are variables, so they have to stay as the variables. All right, so now next thing we want to do, all right, we want to take the derivative. All right, so let's take the derivative. All right, so derivative of W squared, 2W times dw dt. Remember, we're taking the derivative with respect to time, plus 2s times ds dt, right, equals derivative of d squared would be 2d times d dt. Yes? All right. So that's good. Now, after we did that, we would want to plug in known quantities and solve. But we don't know all of the stuff that we need to know in order to solve for dt. Remember, dt is the only thing that we want to remain as a variable at this point. But we know dw dt, right? That's 300. We know ds dt, that's 240. But what about w, s, and d? Well, you have to go back and you have to think. We were told that the south flying plane was flying for 1/3 of an hour, correct? So think about it. If it's flying at 240 miles per hour, then S is going to be 240 miles per hour times 1/3 of an hour, right? In other words, S is 80 miles, right? 240 times 1/3, or 240 divided by 3, right? So if S is 80, that means the southbound plane has flown 80 miles, right? All right, but what about the westbound plane? Well, what would the westbound plane, uh, how far would it be? Well, we would take 300 times the amount of time that it was traveling for half of an hour, right? So 300 times 1/2 is 150 miles, all right? And so now, knowing S and W, we remember that W squared plus S squared is equal to D squared. So that means that W, 150 squared, plus S, 80 squared, equals D squared. Now, I understand, okay, you could use Pythagorean theorem, right? Square those, add them together, square root, right? But this is also just an 8, 15, 17 right triangle. So D would be 170, however you cut it. And so now we know S, we know W, and now we know D, right? 170 miles. And so we can put those pieces in and solve for dt. All right, so 2W, so 2 times 150 times dw dt. What is dw dt? The rate at which the westbound plane is flying, 300 miles per hour, plus 2 times s. S would be 80 times ds dt, 240 miles per hour, equals 2 times d, which is 170, times d dt, right? And so now this is actually really easy to solve because, well, all you're going to do is divide by 2 times 170. So d dt is 2 times 150 times 300. So I'm just going to write this all out, plus 2 times 80 times 240, right? And then all divided by 2 times 170, right? So now we have solved for d dt. Of course, we would want to do some sort, a calculation or whatever. I can make this easier. I can, reduce by 2, and then I've got 170, 150, 240, right? We could reduce all of those, in the same way, dividing everything by 10 or whatever, right? But when it comes down to it, you would have to, if you wanted to simplify this further, you would have to do a calculation of some sort. All right. And so that would be the rate at which the two planes are separating. Now, what are the units? Well, remember, our unit of distance is miles and our unit of time is hours now. So we would get a number of miles per hour. All right. And so that is slide number 17.